as you probably know, that the textbook explanation about the control sequence is rather informal. Not that it is incorrect, it's totally correct, okay, but not very precise. I think that I think it's a kind of intentional in the textbook, will not go in more precise manner because it's too much detail. So I decided to complement the explanation of the textbook there. So, I built this simulation with a detailed control. Okay, boom. Let's see. Okay, and is it exactly the same data path as the one we have learned? Okay, the slightly different things here is that I put in the name, so I can really explain in specific point where things happen and when. Okay, so I have to say something like the address one here, and have some gray box which hold the value. Okay, so you can see that when things happen, how long the information is available because it's important. Okay, right? So something like the output from instruction memory will be whole here. Okay. This is just for our internal use. Okay, the actual circuit depend on the person who built the circuit. It can be built in many different ways. There are two output ports from the register bank. Okay, then I give the name R1 for one port, R2 for another port. So we know when the value is valid and how long that information lasts. Okay, and also give the name of multiplexer. So it can say which multiplexer do what. And also the same for arithmetic logic unit. I give the name. Okay, the output of ALU. And the same for the data memory. The main RAM for us is a memory output. The control signal itself is exactly the same as in the textbook, in the red, now in the red color for easier to see. And also I also label which port of the multiplexer. So you know when the multiplexer select port 0, it select a PC plus 4 here. And if it select 1, it select PC plus offset here. So this level of exactness, okay, it is what I want to include in this explanation. You can imagine it is a kind of complement to explanation in the textbook. Okay, okay, you can see the data path here and the control sequence diagram. Timeline is across, okay, on the horizontal, and it is not to the scale. No, for execution we have fetch, right? Decode, execution, do the memory, and write back to the register. Okay, that is the 5 stage that the data path did to execute one instruction. With this diagram divide into 5 parts. Okay, right? And the event happen from top to bottom. Okay, so you can read this, and you know exactly when it happened and where it happened. Okay, now it say when that control has been asserted or have been active. Okay, and the horizontal blue line show you the information available. Explanation tell you kind of thing that happened at that time. Okay, and when I say that the horizontal line is not exactly scale, register is an internal memory, so it's very fast as well. It's much more than 10 times faster than RAM. I think the memory may not be this fast. I guess maybe actually quite slow because it's nothing we can do. Okay, this is RAM. Okay, this is RAM. So it's not as fast as register. So I would say fetch is not too fast, because it have to get from the RAM, and memory is not too fast because it get to the RAM. So maybe this portion of time in executed circuit will be larger. Okay, but when we draw it according to the information flow in this data path from left to right. All this circuit perform synchronously, depend on the change, depend on the master clock. And who is the master here? The control unit is the master. So that's the preliminary. Now the actual explanation begin. Okay. So 5 stage, all the instruction have to execute these first 2. Okay. You read the instruction memory to get the instruction, right? So the PC on the left side then is already at some number. So it read the instruction memory. This information is stored in kind of temporary, depend on how we actually build a circuit, called the register, instruction register, which is the output from the instruction memory is valid until the end of the cycle. When the instruction available is all bits of them, all 32 bits. It have opcode, have some designated the register. You can have a look at the format in the textbook, have to be decoded. You can be sure that it is a kind of combination logic. Okay, and it become a small number, right? Like a 3 number for register bank. One is which register as a destination, which register as the first source, which register as the second source. To use, if it is a branch instruction, it also have to compute the offset. But we don't know yet whether it will branch or not branch, because we haven't executed the instruction. So just the offset have been completely compute. Compute means it goes through some combination logic and have the output. Okay. And also the immediate value, just like add immediate. It's 12 bits of immediate value will be computed and extended into 32 bits. Instruction memory, instruction already available here on this wire. Part of them go to control unit. Actually, control unit start its work from the beginning, right? To fetch instruction, it has to be under the control unit. And there's a lot of wire going out, right? One is go to 3 of them go into the number of the register, okay? And 1 of them go to immediate, right? And then the immediate go to this one to be fed into arithmetic logic unit. Depend on this multiplexer we call multiplexer 2, okay? Which is controlled by control unit. We call arithmetic logic unit source, ALU source. And the other one, right, and it computed offset. Actually, this offset is quite complicated. So the offset here. So once we decoded all the information is already available, the PC plus 4 already available, the PC plus offset already available, right? Ready to be decided. Register type instruction is not branch. We choose just next instruction to be fetched. If it's branch, it have to be decide whether the branch is taken or not taken. We will explain that later. But right now, right, we are at this line of time on the vertical. I move my mouse. So all this information already available. Okay. Then the execution start. Okay. Of course, once you decode it and information available, you start to read the register bank. So there's no extra control have to be done. Okay. So one is registered, control unit already issue to read. So we read both two register at once, the port R1 and R2 already valid. Okay, so we have two value of register, is each 32-bit available. The first two stage, all instruction and execute the same step. The next step, the next three steps depend on what instruction is fetched. Okay, so if it branch, then it behaves differently from the register type. Okay, and even though it register type, whether it's a will be operate on two register or one register, and the immediate value is different. Okay, and if it load and store register type, then it will be active in the memory stage, and the write back depend on which value to be write back. Okay, let's start with the execution stage. Arithmetic logic unit source choose the value of register 2 to go through the ALU, or the immediate value to go through. If it's a branch instruction, the branch address, okay, we will choose if the result of the arithmetic logic unit is true. Okay, it depends on how arithmetic logic unit is used, but the signal output in the textbook called 0. Okay, and then if it's true, then the jump will be taken. So the PC will be updated by PC plus offset. If it's not jump, then PC will be updated by PC plus 4. And when that happens? At the end of the execute cycle, right? How the PC is updated. You remember the D-type flip-flop? PC is exactly the D-type flip-flop. So we clock the PC, then the information on input of the D will be getting into the inside the register. So this is how it updates. So somebody have to issue the clock to program counter. Okay, and that's the task of the control unit. The ALU perform, right? It's combination logic, maybe 10 nanoseconds. Okay, so the beginning of the output of ALU is a bit later, and it is valid until the end of write back. This simulation is contains 4 branch instruction. Okay, next stage is the memory. This stage will be inactive if the instruction is not load or store. If it load, then it activates the memory read. Okay. If it store, then it activates memory write. How to compute the effective address, right? Because it has to read one register and one immediate value to be added together. So very easy. You can recognize that the address of the data memory comes directly from output of the ALU. We use arithmetic logic unit. Okay, we can read one register here, and we can read we can add with the immediate value, selecting by the source control here to choose the immediate value. It's just like add immediate, right? But now the thing we add is interpret as the address. So we have the effective address here, and we issue the read. If we choose write, then effective address is the same, and the data already directly wired from register number 2. I think register number 1 is a base address for the load instruction. Register number 2 is the source register to be write to the memory. Okay, we will talk about the write back. Okay, and the last stage is we have to update the register. Okay, the destination register. We have the wiring of the output go directly to the register bank, and to activate writing of updating the register bank. This information can come from 2 sources. One is just from the memory, which is we call mout, right? This one must be the instruction load. And if it's not load to register, then it has to be some register type instruction, right? Choose the value of the output of the arithmetic logic unit here. Whether we choose memory or register depend on this control. So that the complete explanation of control sequence when it happened and what happened. Okay, we can specify it precisely using the kind of notation. So I name the functional unit. Okay, right? Program counter, instruction memory, register, arithmetic unit, and the data memory. Okay, and some of them implicit of the control. Some of them, as I already told you, the internal. So the internal value. Okay. Actually, it's a kind of register. And the register have only one control. Okay. And it also has the internal value of R1 and R2. And the LU have LU op control to select the function of LU, and it has the output. This is the output and the 0 bit. Okay. And data memory is okay as usual. And we have the 3 multiplexer, and we designate okay which input connect to what, and then what kind of control. When we want to specify rather than explain in English, we have to write down. So I choose to write down in some kind of pseudo code. So we start with the instruction 0. And in the loop, we do this 5 stage until it stops. The condition of stop is depend on how we implement it. Once we encounter the 0, instruction 0, it means no operation. Okay, and we stop. So the first overall picture is very simple. The notation of explanation is slightly changed. We use this kind of language, A to B. This means signal transfer from A to B to some kind of Y. We call this a kind register transfer language. It has many notation, but I decide to choose this one, A to B. And especially is the notation say A to B semicolon C. It means A to B and C at the same time. There's 2Y going to, one from A and 2Y going to B and C. Okay, so it occurs simultaneously. So what the fetch does is just to read the instruction memory and put it into IR. Okay, and decode is this one. From IR, all the value of the Y is updated. Okay. When we wrote the simulation, we have to give the name to the Y, and the Y become a variable, a global variable. Have to update information on the multiplexer. Okay. Okay. So this connect immediate value to the multiplexer, and then this multiplexer 1 is the branching multiplexer. So it connect the value of the next branching, and now the interesting thing happened. Okay, I choose select control vector. I call control vector. So let me show you what the control vector is. So this is a control vector, a kind of the list, right? We have 1, 2, 3, 4, 5, 6, 7. It's a control signal. What it does is arithmetic logic unit source. Okay, LU operation, and we have this 8 function, right? And I did not implement the first 2. Okay, so we can do add and subtract. And how about the branch? Of course, we have to have the comparison logic. In the textbook, when it branch equal, it just subtract. But I say, okay, let's have the function of, because we have to do not equal, less than, and less than if we use arithmetic, it will be tricky. Okay, if we subtract it, the result is negative, and then we do something. And the branch instruction, if it branch instruction is 1, because it select the multiplexer, and if it is not branch instruction, is 0. Okay, and read write, this should be mutually exclusive. Okay, should not be one both. Okay, it can be 0 both, and it means I don't do anything to the memory, but cannot be both read and write. Okay, and the memory or register is a selecting of the value to update the register bank, and then the write signal. Okay, so 1 is active. Okay, this is an explanation of what we call control vector. So each instruction have different control vector. This is my own interpretation of the how to simulate the RISC-V control. Okay, for add instruction is R type, so we want to use both value from two registers. So A source is 0. A source is 0 is, I think it's 0 select the R2. If 1 select the immediate value. Okay, so first is select the R2, and operation is add. It is the certain, it is not branch. The fourth is it is not a memory instruction, right? And then 0 is mean it choose the output from ALU, and then it write back to the register. Let's do add immediate, which is very similar to add, but select different value for adding. So the first is select the immediate value, and then ALU is add, and then it is not branch, it is not memory, and it choose the output from arithmetic logic unit to write back to the register. And the rest, I left it at your exercise. Okay.